Good day everyone. Welcome to my presentation. I am Captain Ron Irani. In this presentation, I am going to show you how to draw a graph, and the graph is basis draft versus displacement. The data from which we will be drawing the graph is presented here. On the y-axis, we will have the draft, which is ranging from 3 meters to 5.5 meters. And on the x-axis, we will have the displacement, which is ranging from 2,700 metric tons to 6,060 metric tons. We have to find the following data from our graph. Firstly, let us start with the graph. I will switch over to the presentation mode just now. At the end of this video, do give a thumbs up, like, share and subscribe to my channel. Also, do not forget to click on to the bell icon so that you get a notification as soon as a new video is posted on my channel. So the first thing that we have to calculate from our draft is the deadweight. The ship's light draft is given as 3 meters and the load draft is given as 5.3 meters. The second thing is we have to find the ship's draft when there are 500 tons of bunkers and 50 tons of fresh water and stores on board. Now to calculate this part C, 500 tons of bunkers and 50 tons of freshwater stores on board, we will have to start from the ship's light draft displacement which is at 3 meters. Part D, when at 5.13 meter draft, the ship discharges 2,100 metric tons of cargo and loads 250 tons of bunkers, and we have to find the new mean draft. Part E, we have to find the approximate TPC at 4.4 meter draft. And part F, if the ship is floating at a mean draft of 5.2 meters and the load mean draft is 5.3 meters, we have to find out how much more cargo can be loaded. In other words, the available dead weight. So let me switch over to the presentation mode. This will take a short time. Please bear with me. I will start the pointer now. I hope you can all see the red dot that is on your screen. So this is data available to us. We have to construct a displacement curve from the following data: draft versus displacement. And from B to F is what is required from the graph that we draw. I have the graph paper here, and we start with the y-axis. On the y-axis, we have the draft, and on the x-axis, we have the displacement. Now, it is very important to note that we have to maximize the use of our graph paper. There is no point in having the origin at this point, thereby reducing our graph to minimum curvature. With this, you will be reducing your accuracy. The smaller the graph, the lesser is your accuracy. Hence, you have to maximize the use of your graph paper. Therefore, better to start from the corner that as I have shown. The next step is you have to write the scale. On the x-axis, I intend to use 5 centimeters for every 1000 metric tons or 1 centimeter for every 200 metric tons. On the y-axis, it will be 5 centimeters for every meter or 1 centimeter for every 0 meters. It's important to write your because on that basis, the person who is going to check your examination paper is going to measure your values according to the scale that you have mentioned. So, our first point, that is the point of origin, is going to be the draft of 3 meters and a displacement of 2,700 metric tons, where I have marked it with a dot, black dot that you see on the corner. The second point is 2,700 on the x-axis and 3 meters on the y-axis. Then we are going to mark off the y-axis as per the scale that has been shown at the top: 4 meters, 5 meters and 6 meters. The maximum draft required is 5.5 meters on the y-axis. Likewise, on the x-axis, we're going to start off with if 1000 metric tons every 5 centimeters. Therefore, when we started on the origin at 2700, the next stop will be 3700, 4700, 5700, 6700. The maximum displacement in the table given is 6060 metric tons. Now we mark off the second spot at 3.5 meters versus 3260 metric tons. We write that value against the dot that has been marked. The next dot will be at 4 meters and 3800 metric tons. The next dot will be at 4.5 meters at 4450 metric tons. The next dot thereafter will be at 5 meters at 5180 metric tons. The next dot thereafter will be at 5.3 meters at 5700 metric tons. And the last dot will be at 5.5 meters at 6060 metric tons. And now we will join the dots to form the curve. Remember one thing, this is not a linear curve. A linear curve would exist if it was a box-shaped vessel, but since it is a ship, it is going to have a curvature. Now, what is required of us is part B. Ship's light draft is 3 meters and the load draft is 5.3 meters. So let us first complete the markings on our graph. At 5.5 meters, we have 6060 metric tons. At 3250 metric tons, we will have a draft of 3.47 meters. At 5.13 meters, we have a displacement of 5370 metric tons. At 3520 metric tons, we have a draft of 3.75 meters. At 4.4 meters, that is part E, it has just been marked, but what we need is TPC at the mean draft of 4.4 meters. To calculate the TPC at the draft of 4.4 meters, we have to take a range of 20 centimeters, which means 10 centimeters above and 10 centimeters below the required draft. Within this range, the TPC will be fairly constant and it will be the same, in other words. So therefore, instead of 4.4 meters, we take 4.3 meters and 4.5 meters, thereby giving us a range of 20 centimeters. The displacement at 4.3 meters is going to be 4190 metric tons, and the displacement at 4.5 meters is 4,450 metric tons. At 5.2 meter draft, we have a displacement of 5,500 metric tons. At 5.3 meter draft, we have a displacement of 5,700 metric tons. And at 5.2 meter draft, we have a displacement of 5,500 metric tons. Now we revert back to see our calculations. Give me some time, please, for the computer to revert back to the slide. So, part B. Part B says that we have ship's light draft is 3 meters and the load draft is 5.3 meters. At the light draft of 3 meters, her displacement from the graph is 2,700 metric tons, and at the load draft of 5.3 meters, her displacement is 5,700 metric tons. Therefore, when we calculate the difference, that difference is called either the load dead weight or the summer dead weight or the assigned dead weight, which works out to 3,000 metric tons. For part C, we have to find the ship's draft when 500 tons of bunkers and 50 tons of fresh water and stores are on board. So for this, we have to start from her light displacement, and we know that the light displacement as per part B was 2,700 metric tons. Bunkers on board are 500 metric tons, and fresh water and stores on board are 50 metric tons. Therefore, that gives us a final displacement of 3,250 metric tons. Now, going back to our graph, we will see that for 3,250 metric tons, which is here, I'm going to highlight it on the graph now over here, we have a draft of 3.47 meters. Therefore, the final draft is 3.47 meters. Now, for part D, the mean draft of the ship is 5.13 meters and she discharges 2,100 metric tons of cargo and loads 250 metric tons of bunkers. So first, from our graph, we have to find the displacement at 5.13 meters. I'm going to highlight 5.13 meters for you and also the associated line with that. Where it cuts your displacement curve, from that point we will drop a vertical down below to the displacement on the x-axis, and we see that the displacement works out to 5370 metric tons, which is what has been written over here. Displacement at 5.13 meters is equal to 5370 metric tons. She discharges cargo of 2,100 metric tons and loads bunkers of 250 metric tons. Now, bunkers over here mean fuel. Therefore, when we add and subtract what the bunkers we have loaded and the cargo we have discharged from the displacement at 5.13 meters, we get the final displacement equal to 3,520 metric tons. Now, taking this figure, we go back to our graph and we have to find our draft on the y-axis, the displacement on the x-axis, 3520, and from that we will find our draft on the y-axis. So let's go back to the graph. 3520 metric tons, I'm sorry. We take a vertical from that till it meets our displacement curve, and from that point we take a horizontal and we see that our draft is 3.75 meters. Coming back to our calculations, therefore the final draft is equal to 3.75 meters. Part E, approximate TPC at 4.4 meter draft. As I explained earlier, we have to take a range of 20 centimeters. That means 10 centimeters over and above 4.4 meters and 10 centimeters below 4.4 meters, thereby giving us a range of 20 centimeters. Thus, the draft which will be higher than 4.4 meters is 4.5 meters, and the draft which will be lower than 4.4 meters will be 4.3 meters. At 4.5 meters, we see from our graph the displacement is equal to 4450 metric tons. So let us see at 4.5 meters, we have the horizontal line going up to the graph, and from there we drop a vertical to the displacement on the x-axis and we get 4450 meters. Likewise, for 4.3 meters, we take a horizontal that meets the displacement curve. From that point, we drop a vertical onto the x-axis and we see that the displacement at 4.3 meters is 4190 metric tons. We use that value in our calculations. Therefore, the difference to change the draft by 0.2 meters or 20 centimeters is equal to 260 metric tons. Now, TPC is, the full form is tons per centimeter. Therefore, per centimeter, we will have to divide 260 by 20 because we have taken it over a range of 20 centimeters. Therefore, the difference to change the draft by 0.01 meters or 1 centimeter is equal to 260 divided by 20, and that gives us the TPC is equal to 13 metric tons per centimeter. Part F of the question is, if the ship is floating at a mean draft of 5.2 meters and the load mean draft is 5.3 meters, find how much more cargo can be loaded. So at 5.3 meter draft and 5.2 meter draft, we have to see the displacements. At 5 meter draft, the horizontal meeting the displacement curve, and from there we draw the vertical down to the, I'm sorry, at 5.3 meter draft, the horizontal at the on the y-axis meeting the displacement curve, and from there we drop the vertical down to the x-axis and we see that the displacement is 5700 metric tons. Likewise, for 5.2 meter draft, we take a horizontal till it touches the displacement curve, and from there we drop a vertical onto the x-axis and we see that the displacement is 5500 metric tons. This we will use in our calculations. Load mean draft 5.3 meters, displacement 5700 metric tons. Present draft 5.2 meters and present displacement is 5500 metric tons. The difference between the displacement at the load mean draft and the present draft will give us the dead weight available of 200 metric tons. Now, I would also like to point out that in this graph which we did, we started with the origin of 2700 metric tons on the x-axis and 3 meter draft on the y-axis. I'm going to show you another graph, the same except that the origin we are starting off with 2403. 2400 metric tons on the x-axis and 3-meter draft on the y-axis. The scale stays the same, and 2700 metric tons is shown over here where my mouse is located. And from there we proceed to mark off all the points, the 6 points that are required, 4, 3, 7 points that are required. We draw exactly the same diagram. For the displacement curve, we mark off the drafts required and the displacements required, or the displacements required and the drafts that are calculated from our graph. If you notice, the graph is exactly the same except that the point of origin is marginally different. Now you would ask me as to why can we not draw the same graph starting with the origin as 0, 0. The same problem I'm going to show you with the origin as 0, 0. Here, because of the non-availability of space, I have taken the liberty of drawing the graph only until 5.3 meters instead of 5.5 meters, and displacement until 5,700 metric tons instead of 6,060 metric tons. Otherwise, the graph stays the same. So, as you see my graph now, starting from the point of origin 0, 0. What happens here is, to be able to draw the graph correctly, marking off all the values on the x-axis and the y-axis, but your accuracy will suffer. You will not be as accurate as if you had started with your origin at 2703 meters or 2403 meters. Secondly, it is also to be pointed out that many students draw this red line, as I have shown over here, from 0 meter draft to 3 meter draft and 2700 metric tons. It being a ship, the increase in displacement is never linear. It is always on a curve. As you will see, if it was a linear thing, then let me just extend this further and you will notice the difference. You see, if it was linear, it would be going this red line that I have extended, but it is not a linear progression. Hence, friends, it is always very important to start off with your very first point being the 3 meters, as in this problem, on the y-axis and 2700 metric tons on the x-axis, or 2400 on the x-axis. I will show you the values that you will get from this curve that I have shown above. And after seeing this slide, you will note the difference because the accuracy has suffered in this calculations that you will see. Thank you very much for your kind attention. Do give a thumbs up, like, share and subscribe to my channel. Also, do not forget to click on the bell icon so that you get a notification as soon as a new video has been posted on my channel. Thank you, goodbye and take care.